welcome to my presentation with the title RISC-V Android Bring Up Using Sim5. My name is Lukas and I'm from MachineWare. And yeah, let's get right into it. So first I want to introduce or give a little motivation for this presentation. So right now there's only very limited supply of Android-capable RISC-V hardware. So it's very hard to buy a RISC-V processor that is able to boot Android. And therefore, we think it makes sense to start Android development early by using a simulation solution. So we want to use our simulator Sim5 for Android prototyping. There are, besides the availability, other advantages of physical prototypes. So I already mentioned, usually virtual prototypes are available earlier. So right now we have the situation that we have a virtual prototype that can actually run Android while hardware is still kind of lacking, which enables a shift-left methodology. So you can start your software development, your software verification, your prototyping today, even though you don't have the hardware yet. Also, virtual prototypes or simulators are extremely flexible, so you can change them in whatever way you like, because in the end they are software, and software can be changed quite easily. In addition, they allow very deep introspection into the state of the system. So in a simulator, you can press pause anytime, and that really completely freezes the state of the simulation, so there are no ticking clocks or anything, and you can dive very deeply into what the simulator is doing at that point in time, for example, using a debug tool like GDB or Trace32, something like that. Besides that, simulators are a lot more scalable than hardware prototypes. If you have a hardware prototype in the beginning, usually you have only very limited supply. So you maybe have a dozen prototypes, and then of course prototype will break, and then you have one less, and then you have even less prototyping hardware available. With the simulator, you build the simulator once, and then you can copy it 1,000 times. And you can run it in parallel, for example, also in the cloud to run your test cases, to exercise your software. And that is why we think that simulation solutions are very useful for software development and verification. Now I want to talk a little bit about Android software architecture. So Android software architecture is extremely complex. At the bottom of the software stack, you have a Linux kernel. So you boot the Linux kernel, but then this can be done rather quickly, but then afterwards you have a huge amount of user space applications that are part system libraries. Then there is the Android runtime, which is in charge of executing the applications. Android applications are actually written in Java, so there's also a translation process in that Android runtime happening. And on top of all of the system libraries and the Android runtimes, you have the application framework that is used by the app developers to write the applications, to hook into the different parts of Android and the different services that Android provides. And then on the very top of the stack, you have all the applications. And there is, of course, a huge amount of applications. And overall, that just means that you have a Linux kernel and then you have a huge amount of user space. And that is difficult to simulate because context switches are they cost performance, they are hard to simulate. In addition, you also need graphics to run Android because you want to look at the output, right? You want to see the screen, you want to interact with it, you want to test your applications. So you also need output, and this requires OpenGL. OpenGL is a graphics library that you need. And so that means in your simulator to run Android, you also need a 3D capable GPU model. And that also has to be very fast. So to summarize the Android simulator requirements, first of all, you need very good performance. If you want to boot Android, like a full Android boot from starting the kernel until using the home screen, is about 100 billion instructions that you have to execute on your simulator to fully run this test case. And I think boot is a pretty normal test case. Then, as I said before, you need a GPU. And it has to be capable of doing OpenGL, so you have to have a 3D capable GPU model. And of course, if you want to use the simulator productively, you also need debug capabilities. So you want to be able to debug the kernel, for example, using standard software debuggers like GDB or Lauterbach Trace32, something like that. You also want to be able to debug the user space applications, for example, the system libraries. but you also want to be able to debug the apps that you are running on top. And for this, Android has a special debugging tool that is called ADB. So you want to be able to use that with your simulator as well. So how do we at MachineWare address these challenges? We have a simulator that is called Sim5, and Sim5 is a fast functional RISC-V simulator. It is about 2.5 times faster than other state-of-the-art simulators, and it enables you to shift left your software development. So you can start your software development early, and you can have better software available earlier. Besides performance, for us, there are two more important design goals in Sim5. We want Sim5 to be easy to use, so we want our customers to be able to reap the benefits of using Sim5 as quickly as possible, so we want it to be easy to use. And also we want it to be easy to integrate, because often when you build an SoC, you don't only care about the RISC-V course, but also all the peripheral models that might come from third parties. So we rely on standardized open source interfaces to interface simulator components to Sim5. And I want to highlight this interoperability fact. So I want to talk a little bit about the interoperability of Sim5. So in the middle, we have a MachineWare CPU model that can be, for example, a RISC-V CPU model like Sim5. And we integrate this into different environments. One environment that we can integrate into is systemc TLM, which is an IEEE standard environment for connecting simulator components. The issue with IEEE systemc TLM is that it doesn't enable parallel simulation. So if you have a multi-core system, you cannot easily parallelize your simulation, which leads to a performance bottleneck. And we have an integration into systemc that allows this parallelization. So with our parallel systemc integration, you can actually parallelize the execution of multiple CPU cores in a fully systemc TLM compatible, standard compatible way. Besides that, we also integrate into other simulation environments, for example, Synopsys Virtualizer using the OCX interface, which also enables parallel simulation. And last but not least, we have our own environment, which we call MachineWare Virtual Platform. When you use MachineWare Virtual Platform to model your system, you get a lot of nice features. For example, as I mentioned earlier, you need the debug capabilities, so we have debugger integrations for standard debuggers. We also have a Python framework which allows you to use your simulator in continuous integration environments. So you just write your test case in a Python script and you run it as part of your CI loop very easily. Of course, we also have some trace and analysis features which allow you to check what's going on inside the platform. And we have peripheral models available that allow you to connect your simulators to standard interfaces like Ethernet, I2C, and so forth, CAN. So how do you run Android on MachineWare Sim5? Well, Sim5 has fast parallel CPU execution, so we can perform an Android boot rather quickly. And we also have a 3D GPU model available that allows you to get graphical output. So basically, you take your Android images, you push them into Sim5, and you get output. We have right now full support for Android 12, but we are also working to support Android 13, which is the version that is coming out now. You can interactively debug the simulator, for example, using our own GUI tool, Viper, Virtual Platform Explorer, but also using standard debuggers like GDB. And I mentioned earlier, we have an integration that allows you to plug our simulator into your continuous integration environment, for example, using Jenkins or GitLab CI or GitHub Actions. So how do we envision virtual Android device verification? So as a user, you use Sim5 and your normal development tools to, for example, work on the Linux kernel that you are using for your Android development or user space applications or libraries. When you do changes in these components of your Android build, you push these changes to your version control server, version control and continuous integration, continuous delivery server, for example, GitLab. This then triggers an automatic build of Android. Android build takes quite a while, so you need a powerful machine, but in the end you get all the components that result from an Android build. A kernel, a RAM disk, a system image, a vendor image, everything that is part of the build artifacts of Android. These build artifacts can then be used in continuous integration scenarios. So your CI server will trigger your CI runners that are, for example, running locally on your own servers, or you can also run them in the cloud. And these CI runners then have Sim5 a test script written in Python, and they will give test results. During runtime, the CI runners will then consume the images that you have built using your VCS. When all the CI runners have finished, you can look at the results. So the CI runner will report your continuous integration results to your CI dashboard, for example in Jenkins or whatever CI solution you use. And then this provides direct feedback to the developer that has made this change. So with our technology, you can test every single commit in your Android stack. Right, so that's it from me. If you are interested in this topic, please come to our booth. We have our Android demo running there. You can check it out live. You can see how it works. And I'm glad to explain more over there. So thank you for attending this presentation.